folks, we'll go ahead and get started this morning with just a couple of quick reminders. PLC 12 is up for Friday, and it's on simultaneity, simultaneity and in special relativity. So that's Friday. And we have homework 7, and I went ahead and said we'll postpone that until Tuesday of next week. So that's going to be, originally we had it on Thursday, which is tomorrow as of this recording. And I'm going to go over some more examples today, and I thought we just don't need to be crunching it quite so close. So Tuesday will work. Give you the weekend, think about it, and we'll go from there. So quiz will happen as usual with that homework, and there was something else I was going to say, but I forgot what it was. Oh, I know. I haven't updated the Canvas site to make that change. I need to remember to do that. So I will try and update Canvas so it reflects this due date rather than the Thursday due date. All right. So there's that, and we're going to go ahead and get started on a couple of examples and see where that takes us today. So one thing I'm going to do is start with a couple more just time dilation types of things, and what does it look like space-time diagram wise, what can we calculate about things, and we'll go from there. And maybe with a little bit of time we can go to looking at the Lorentz transformations, and we can go to some velocity additions and maybe a little bit of GR today. So I think ultimately this will be our last day of the SR. All right, so what we'll do is take a look at just another out and back journey, and taking a look and see what kind of times and comparisons we can make. So let's do this. Spaceship. Alrighty, so let me see here. All right, so we'll start with an example here where the spaceship blasts off from Earth, and it takes off towards a distant star, and it's going at 0.95. So when the spaceship turns around, comes back to Earth, the clocks here read 80 years. So question of how much time has elapsed on the spaceship clocks. Okay. Now, first thing we want to do here is draw a space-time diagram. Okay, so what time does the spaceship clock read? Let's draw a space-time diagram first. If this was like a quiz or celebration problem or even a homework problem, that would be kind of the first thing I would say here. Draw a space-time diagram of the trip and point out what's going on. So let's go ahead and do that so that we can get an idea of visually what does this look like. So remember that the idea of the space-time diagram is that we see both frames on one plot, okay? So that means I'm going to draw the space-time diagram as seen by Earth, and then I'm going to draw the space-time diagram as seen by the rocket ship, and we are going to do those on the same set of axes, or on the same plot here, and we can go back and forth and interpret between the two frames. So at 0.95, what we're talking about here is something whereby 45 degrees looks like it's about, say, here. So 0.95 is going to cause these axes to be pretty squinched up to that, which means we're going to be going like, oh, this pen's dead. I wanted a different color here, and I forgot my own pens, so let's see if I got one over here. Oh, that's dead too. Alrighty. Okay, I guess we're just gonna stick with the black then. Now, that means that the 0.95 is going something like this. Alright. I'm gonna extend this out a little bit further so I can label that the T prime axis. Now that would be, that's curving upwards a little bit, sorry. That would be the outbound journey of the spaceship. Okay, that would be the outbound journey of the spaceship. But at some point at the distant star, it flips around, it turns around, it comes back, which means it's going to be coming back kind of like this. Whoa, all right, this would be the T double prime axis, which means it's now on its way back. And so we're dealing with 3 total frames here inertially. And we're gonna actually have the ability to look at all 3 of them on the same plot. Okay, so the outbound journey is the T prime axis here. Now notice that in the Earth frame, that's going to be what's called the world line of the spaceship as it leaves. Therefore, according to Earth, that distance would be the proper distance from Earth to the star. Reason being that Earth and the star we can assume are in the same reference frame, and therefore the distance between them, it will be properly measured by someone in the Earth frame or the star frame because they are at rest with respect to the Earth and the star. So we will be able to measure the proper length between those 2 things. The rocket ship observer will not measure the proper length. However, the rocket ship observer will be measuring the proper time between the event of leaving Earth, arriving at star, leaving star, and arriving at Earth. The rocket ship will measure the proper time of that. So, what we know is that the clocks read 80 years. So, at this point here on the space-time diagram, here on the Earth axis, this will be 40 years. That's halfway between. Up here when the spaceship rejoins Earth, that's the 80-year mark. All right, so I'm just using Y for years. So question of at what reading on the spaceship clock do we have when the Earth clock is reading 40 years? All right, so this is a situation where we're going to look at time dilation. All right, and we know there's a time stretching factor. So T on Earth is going to be longer than, oops, I need my gamma. Where's my time stretch factor here? I need my time stretch factor times delta T on the rocket. I meant, or spaceship, whatever it is, rocket. All right, so that's our time dilation. Now, why are we able to write this down? Because we know that the person on the rocket ship measures the proper time. Now, the proper time, people will agree on what the proper time is. The proper time is always the shortest possible amount of time that has happened between the two events. Reason being that, why is it the proper time? It's because the proper time is the one in which there is no movement of the clock between the two events. And you'd say, well, that's not true. The rocket blasted off from Earth and it went all the way to the star. Right. From our reference frame on Earth, it did that. But from the rocket's perspective, what happened? The rocket's perspective stood here. It said, I'm looking at my watch. Earth is now going that way. And the star or the planet or whatever is approaching me. And it arrives. And my watch has not moved between Earth and the star because Earth went that way and the star came this way. And those two events happened right here. And the clock didn't move between them. As soon as you carry a clock between two events spatially, you cannot be measuring the proper time, okay? Since the proper time is measured by the person on the rocket, and the proper time is always the shortest, then we're always going to stretch that time out because gamma, we're going to stretch that time because gamma is a number that's greater than 1. In this case, we're going to have to calculate at 0.95 what gamma is, so let's go do that. I'm gonna have to, let's see, I forget how much I forget what it is. It's like 2.3 or something, I forget. So we'll do 0.95 and we'll square that number and we'll add 1 to it and then we'll square root that number and we'll flip it over. And it's 3.2. So the calculation of gamma being square root of 1 minus v squared, 1 over that, with v being 0.95, I get 3.2 for that number. And that's just a unitless factor. And we're going to say then that the Earth time is 3.2 times longer than the rocket time. Since we're looking for the rocket time, all we got to do is flip this around and say that it's, so let's suppose that it's a one-way journey. Okay, let's take that back. It's not a one-way journey. Let's suppose I'm only going to calculate it for a one-way, and that way I will know what reading appears at this point on the t prime axis. So this is going to be 40 years divided by 3.2. Let's see, what's a number that's about 8, 9. 9 is pretty close. Not close enough though. 10, 11, 12. Maybe it's about 12.2. So 1/5 of 12 is a little over 2. So it's about 3. So 39. So let's call it 12 in a little bit of years. 12 point something. Here, I'll be good. Call it 12.5. All right, so 12.5 years. That means a grand total of 25 years has elapsed on the rocket, and the person on the rocket is 25 years older, but people on Earth are 80 years older. Right, so right here, I would say that's a t prime of 12.5 years. That's the time on the rocket ship. Let's try to calculate how far away the rocket went. All right, so how would we calculate that? I've got multiple amounts of time. I've got a speed here. I'm looking for a distance. What if I'm trying to calculate this distance right here? That is to say, what's the proper length between Earth and the star, the distant star? We can calculate L, Because ultimately, from Earth perspective, what we're doing is we're standing here watching a spaceship leave at constant speed and going for a known amount of time, which is 40 years according to us. Therefore, distance equals rate times time. So this is 0.95 multiplied by 40 years. 0.95 times 40 years. So that's going to be 30. What is that? It's going to be 36 plus half, so it's 38. It's 38 light years. Let's see if I got that right. What did I say it was? 0.95 times 40. Yep. So this is the speed times the time. So as seen from Earth's perspective, that distance to the star is 38 light years. Now, wait a minute, you'd say. How can a starship travel 38 light years in 12 and a half years? Even light would take 38 years to get from Earth to a star that's 38 light years away. In case you're not familiar with the light year unit, it is a distance unit, and it encompasses the distance light travels in 1 year. So just imagine a light beam just zooming along for a full year, and it's that distance. That means that it takes light 1 year to travel 1 light year. So how can a rocket ship have traveled 38 light years, which should have taken 38 years if you were on light, which is supposedly the fastest thing we know about, except this rocket did it way quicker in only 12 and a half years instead of 38. So this rocket ship must have been going way faster than light speed, right? Or wait, what's going on? I'm falling into a trap here, okay? What I'm doing is I'm comparing measurements from 2 different frames. This is from the rocket's perspective, okay? This is from Earth's perspective. So those two do not go together, okay? If I want to think about a speed, then I got to think about a distance in Earth's frame and a time in Earth's frame, or I think about a distance in the rocket frame and a time in the rocket frame. So the question might be here, okay, how much time is the rocket, sorry, not how much time, we know how much time that rocket's experiencing. What distance does the rocket measure between Earth and the distant star? Well, you can probably find, based on what we talked about yesterday, that as Earth leaves and the distant star approaches, remember that distance is contracted. So we would find, so this is really Earth, this is Earth's distance. If I wanted the rockets, if I wanted the distance between the Earth and the star as measured by the rocket, I would use L of the Earth divided by gamma. Or I could also likewise say Earth and the star were moving at 0.95 relative to me here on the rocket, and my watch read 12 and a half years. So it would be 0.95 of 12 and a half. That would also be a completely valid way of doing it. Or you can use the length contraction like this and find out that it's 38 light years divided by 3.2. Well, if it's 3.8, it would be 10. So it's a little bit more than 10. So let's say it's 10.4 light years. And now what you're seeing is that the rocket sees that it traveled 10.4 light years in 12 and a half years, and that hopefully makes things a little bit more copacetic, because the minimum amount of time it should take would be 10.4 light years to travel 10.4 light years. Okay. All right. So this is what the space-time diagram looks like, and those are the relevant quantities and how to calculate them. Let's move to another one that's a little bit on the slightly more involved spectrum. And let's take a look at this, in which I have a meter stick traveling, say at 0.5, and I'm going to draw a space-time diagram for it as it moves past me and calculate how much time it takes for the meter stick to move past me. Ugh, gross. Lots of ink that gets spread around here. That looks terrible. All right, let's suppose I got a meter stick moving at 0.5. How much time does it take to pass me? All right, as usual, first thing is draw the space-time diagram. All right, so let's assume then that we're going to have the front of the meter stick being right near me, and we'll say we're going to synchronize our clocks, or we're going to both reset our watches at time to be 0 when the front of the meter stick is passing my origin, and our origins are coinciding. So let's assume that the x and the x prime, that means I'm going to need to extend this a little bit back here. Let's say that the x and the x prime are 0, right, where t and t prime are 0, and the front of the meter stick is there. So moving at 0.5, here's my 45 degree line. So moving at 0.5 is probably something like that. There's the front of the meter stick. The back of the meter stick is over here, doing the same thing. Well, I'm gonna have to put this up a little bit further, like that. So the back of the meter stick is going, I'm gonna incline this a little bit more. We're gonna go here, okay. Like that. Are those about parallel? Hopefully. So let's call that T prime. This is the front. Of the stick. This is the back of the stick. Okay, so those are the world lines of the front and back of the stick as they move relative to me in the earth frame. T in the earth frame, T prime is the meter stick frame, and what we would be interested is how much time does it take to go past? Well, the front of the meter stick is here at time 0. How much time, according to the earth frame, does it take for the meter stick to go past? Well, the back of the meter stick passes by the x equals 0 point there. And so I'd be interested in what's the reading on the clock at this point. All right, so I'm looking at the earth frame, that's this axis here. What's the time reading on that frame when the back of the meter stick passes by? Okay, well, this is, let's sketch out what we want to do. Remember, this is special relativity, and that means things travel at constant velocities. So the meter stick is going past, and it reaches a certain point here, right? Bump, and then it bump, and it keeps going, okay? Now remember, I do not measure a 1 meter length of the meter stick because the meter stick is in motion with respect to me, therefore I measure its contracted length. So if I want to ask what time it takes for it to go past me, I would say, well, the time as measured on Earth would be equal to the length of the meter stick divided by its speed. And we know its speed is 0.5, so that's not a problem. The question is its length, however, is not 1 meter. This is a contracted length. Length on Earth is contracted. Therefore, what we have to do is write that the length as seen by the earth frame is really the stick, length of the stick as seen in the stick frame divided by gamma. Okay, so that's the contracted length just shoved into that fraction there. And at 0.5, let's see, 0.25, 0.75, what's this going to be, 1.3? Let's take a quick look at the calculator here. All right, this is going to be. Where's my squared button? There it is. Yep, 1.3. This is equal to 1 meter divided by 1.33 times 0.5. Since this is 4/3, and that's 1/2, so I can get rid of that and say it's 2/3. So this is equal to 1.5 meters. Which I guess kind of makes sense. Let's see, does it? 1/2, 3/2. Yep, so it should take 1.5 meters worth of time to go past me. Is that true? It seems like it should take only 1 meter's worth of time to go past me. But it can't, because the question is what distance do how much do I measure the meter stick in my frame? So apparently in my frame, I'm going to measure the meter stick to be 0.75. That's why, right? In my frame here, L Earth, right? L Earth is everything in here without the 0.5 on the bottom, which means it's 3/4. So that's right? Yeah, 0.75 meters. So what I see from my perspective is a 3/4, well, let me put it this way. I measure it to be 3/4 of a meter long, moving past me, and it's moving at 0.5, which means light's going double as fast as the meter stick is going, and therefore light's going to have gone double the distance that this did during that time. So the time it took the meter stick to go past me at this amount, right, with this shortened meter stick, the time it takes that to go past, if it was traveling at light speed, would be 0.75 of a meter. But it's traveling at half light speed, which means the time it takes to go past me is 1.5 meters, because light will have traveled 1.5 meters in that 0.75 meters worth of time. So if you wanted to change this out and say, okay, but what's the time, right? If I don't have a clock that reads in meters, so what am I supposed to do here? What you're supposed to do is then change the time in meters to a time in seconds, and we have a universal factor to do that. If I wanted that in seconds, I would say delta t in seconds. This is delta t of Earth equaling 1.5 meters. I would have to divide that by 3 times 10 to the 8 meters per second, so that I can flip the seconds up on top and get a time. And then I would be able to tell you what that looked like as a time in seconds that would be measurable. So this looks like it would be somewhere in the hundreds, no, in the tens of a microsecond or so, something about like that. 1.5 divided by 3 is 0.5, actually 10 to the minus 8. No, sorry, I take that back. It's in the tens of billions of a second, somewhere like that. So it's fast, but we can measure things that are that fast. That's not a problem. Okay, one other piece to this. If I'm measuring the contracted length as an Earth observer, then what I'm saying here is that this distance right here is really 0.75 meters. That's not 1 meter. Okay, because I'm not measuring the 1 meter stick. I'm measuring something that's a contracted 1 meter stick. So where is the true length of the meter stick? Well, the true length of the meter stick is observed by the meter stick's perspective, which means that it would be this distance here. If I'm going to say the x prime axis is something like that, then it's going to be something like this. If I made a simultaneous measurement that would be 1 meter as seen by the meter stick, because in the meter stick's frame, the meter stick's not moving and I can make simultaneous measurements of its two ends, okay? So therefore, with a simultaneous measurement, it's got to be parallel with the X prime frame, and it doesn't look like I quite managed that, so let me try and draw that again. It's going to look like that. Okay, maybe it's like this. This is the X prime frame. I'm trying to make this parallel with the space axis for the meter stick, such that what's happening is simultaneous things at the front and back. It's taking a simultaneous measurement front and back, and we know simultaneity is always parallel with the space axis. Okay. Alrighty. So how much time does it take to go past? And there you go. Let's look at one more in which we have, this is a little bit strange, but you know, what you do with the stuff you learn when you have kids is pretty amazing. Let's get rid of this. So we find out, I'm reading a is it National Geographic? No, something else. Maybe it's Ranger Ray. I don't remember. My daughter she really likes animals and nature and stuff like that. So she's finding out all this stuff about elephants. So she finds out that, humans have babies in 9 months. How long does it take an elephant? And the magazine kind of talks about it. Well, apparently it's 21 months for an elephant. And how is this useful, you ask? Well, let's suppose that we take an elephant that is going to have a baby. And it's going to be 21 months for the elephant to have a baby. But we're going to take the elephant and we're going to put it on a rocket ship and blast it off. And so we're going to ask the question, how much time on Earth elapses before we expect to hear via radio communication or something like that? Whoever's on the spaceship says, listen to the squeals of the new baby elephant, and sends it back. At what point do our clocks say, aha, now we've heard this? Well, right, how much time elapses? So let's suppose that an elephant, which takes 21 months to have a baby, and it's on a spaceship, and let's suppose the spaceship is traveling 0.8 at 0.8. What do Earth clocks read when we find out about the baby getting born? All right, so what does this mean? Well, what this means is we've taken the elephant, we've put her on a spaceship. The spaceship's flying away. When the elephant gets born, right, they have to radio the signal back. So we have to take into account all that time. What does this look like? Well, here's my C line, and let's suppose that my T prime line, so there's the spaceship, okay? And what's going to happen is the spaceship is going to radio back, hey, we've got the baby elephant, and it's going to take time for it to make the journey back to Earth. But that means I'm going to take a light signal. Suppose the baby elephant is born right at that point. We do everything instantly, so don't worry about time. Oh, we got to look at the baby elephant and take some pictures. No, as soon as we know, we're sending it back on the information. But that means I'm going to draw a 45-degree line straight back up to the t-axis, which is where we are. So let me see if I can get a 45-degree line, which makes maybe like that. And it's going to there. So I want that time right there. That's a light line. Okay, so that's a 45-degree line. So the question is, when we put the elephant on board the spaceship and after we receive the radio transmission about the baby elephant, what's the time on Earth? What's our clock reading? All right. All right, so let's take a look. This point here is when the baby's born, okay? So on the T prime axis at that point, we know the time right there is 21 months. So the question is, what's the time on Earth? Let's try and find the time on Earth that that 21 months corresponds to. And then we have to find out how far away the rocket ship is at that point, so such that when they then send a signal back at light speed, which is 1, so that'll make it easier to calculate, we just have to then add that on to how far the rocket ship's gone. All right, so this is the time of birth, I'll call that TB. And then this time here, this is supposed to be my axis, so I'll put that there. And I'm curious about that. That's TB plus time of L, which is the light to go. All right, that's what I'm interested in. So TB is the time as seen on Earth. And the 21 months is now the proper time because that's the time on the rocket ship. And the time on the rocket ship is baby elephant. We got on the rocket ship, Earth blasted off, and the baby's born, and it hasn't moved, so rocket ship has proper time. Therefore, I have to calculate gamma and use T on the rocket, which means 21 months. Gamma is going to be, let's just figure out gamma real quick here. Gamma is going to be square root of 1 minus 0.8 squared. 0.8 squared is 64, so 1 minus that's 36. Square root of that is 6, so it's, darn it, 10/6, which is 1 over 0.6. It's 10/6. Oh, I wish I had picked something different. Oh well. It's 10 divided by 6 multiplied by 21 months here. What's that going to be? It's, well, 6 would put you at 18 and another 6 would put you at 24. So I guess it's 3.5. So we're going to measure 35 months on our clocks. So TB is 35 months. 35 mo. All right. We now have to wait for the light signal to come back, which means we have to calculate how far away the ship is at that point. Because if we calculate that, then we'll know if we multiply it, or if we take that distance and then divide by 1, we'll have the time it takes for the light to get back. And that means that at 35 months worth of travel, the distance away that the rocket ship is, as measured in Earth's frame, is 0.8 times that number. 0.8 times 35, 8/10. So that's what, I don't know, 36. Now I'm starting to fail. 36 is close, and 0.8 of 36 I should know, but I don't off the top of my head. So 0.8 times 35, and that's, oops, 28. I feel I should have known that somehow. 28. So this is 28, whoops. Whoops, nope, try it again. All right. So this is 28 light months. In other words, they are as far away as it would have taken light 28 months to travel. They, however, traveled 35 months in order to get that distance. Therefore, we take the 35 months, we say, how much time does it take a light signal to get from 28 light months away? Well, it takes 28 months. So we're going to add the 28 onto the 35, and we're going to get 63. So TB plus TL, so this is TL, is then going to be 28 months. And therefore TB plus TL is 35 plus 28 months, which is equal to 63 months. So that's this is not 2 years, but a near 2-year gestation period, and we didn't find out about it until 5 years later, more than 5 years. So anyways, so that's kind of how you work around things like this. Make sure you are keeping things in one frame separate from things in another frame, right? You're always thinking about, here's what's happening on the rocket ship, here's what's happening on Earth, and keep them separate, and try not to let them mix. All right, good. So what we'll do here is we'll go to this now. Well, what do we got? Yeah, all right. So let's talk a little bit about, I think that more or less finishes off what we need to know for special relativity and the corresponding homework set. So let me go in and take a little bit of a look at what's going on with some other stuff. I thought it'd be interesting to talk a little bit about GR with time permitting here. So if you're interested in general relativity, you can stay on for a little bit longer, and if not, then you can go and do something else. I'm just paging through to see that I've gotten everything that I need to here, and the answer apparently seems to be yes. All right. So let's talk a little bit about GR. All right, so actually, before we do the GR stuff, there's one other thing I think that I need to talk about before I say that SR is over for us, or at least we've done what we need to. I got to talk a little bit about energy. So I think with special relativity, I do have to say this is a bit of an oversight that I forgot about this, but energy in special relativity is basically one of two types, and this is probably, I'd have to guess, this is probably the most famous equation that there is. I don't know. Equals mc squared? I mean, who doesn't know that? Now, notice that this is not in our system of units. We would have just had E equals m because our c is 1. So typically we would have just said, well, E equals m, and that's done. But what that's getting at is something interesting, which is that there's something known as mass energy. And the mass energy of something can be calculated by looking at what this is. So if you wanted to calculate the mass energy in typical human units, you might want to look at joules or something like that. So you take your mass in grams or kilograms and you multiply by C in meters per second, and then you'd be able to square that and appropriately make things look like a joule, so that you could get some energy out in joules. And that's just the energy that the thing has in that's bound up in its mass. Okay, so you say, well, how do things with mass have energy? It's an energy equivalent. Yeah, it's an energy equivalent because ultimately, and this is part of what gives rise to the particle physics field. It's the idea that everything's made up of something, right? Now, if you look at, you say, well, I'm made up of cells. Okay, great. But cells are made up of molecules, okay? And molecules are made up of atoms. And how are they made up of these atoms? Well, they're bound together. So what does it mean for something to be bound together? If it's bound together, that means it takes energy to rip them apart. And that's kind of what we're talking about when you say there's mass energy. There's energy in the bondings of these things, okay? And then you take other things apart, and you take other things apart, and you take other things apart, and you're finding out that when you bind things together, the masses of the things, there's energy involved there, okay? Even down to the point where you can go the other way and say, well, I've got a bound system here. If I take the two things apart and I weigh them, they'll have a different mass individually, right? Such that if I added those two masses and put them back together in a molecule, I'd have a different mass of the molecule. That's because there's binding energy involved here, and now the molecule does not weigh this plus this, okay? So there's energy wrapped up in mass, and also there's a mass equivalent of energy, okay? So in special relativity, there's mass energy, and then of course there's also kinetic energy because things have to be moving. So kinetic energy goes this way. Essentially, this is the mass energy of something when it's not moving with respect to you. Okay, so the total energy of something in special relativity is essentially wrapped up in total energy E. I should maybe have called this E naught or something so that you're not moving. Is essentially gamma times, if you like, mc squared. Or for us, it would just be gamma m. The mass energy is the m part of it, which means that there's one left over, and therefore the kinetic energy is gamma minus 1 of that. In other words, it looks like this is an mc squared plus a gamma minus 1 mc squared, right? So in other words, if I add the mass energy to the thing, right, if I take this out, what I'm doing is I'm subtracting off an mc squared here, and I can factor that out as a gamma minus 1 here, multiplying the mc squared. Therefore, this must be the kinetic energy. And that's going to help you on the problem with the energy. I think that's going to help you on the energy of the electron in a relativistic sense, because wrapped up in the gamma, of course, is the speed. And since we know what mc squared is for an electron, if, by the way, you don't know that, mc squared, in other words, the mass energy of an electron, for an electron, this number is going to be 0.511 MeVs. And an MeV is 1,000,000 electron volts. So you can use 0.511 MeVs for the mass energy of the electron. And typically when you get into these particle type things, that's just, you don't even say energy anymore. You just say it's the mass of the electron is 0.511 MeVs. Because they are basically the same thing, right? For us, energy is the mass. All right, well, there's more you can say about this, but ultimately, I think that's all we really need to worry about. Okay, so maybe at this point we'll start talking a little bit about GR. Let's do this. I want to go from the special relativistic situation, which is a constant velocity, no acceleration type of scenario, into the GR situation, which is exactly what Einstein did. Einstein wrote the SR paper in a matter of maybe 2 or 3 months, or actually it wasn't even that long. It was probably like 1 month, okay? But then it took him over 10 years to accomplish general relativity, which is to say accelerated motion. That's not trivial. If it took Einstein more than 10 years, well, we don't have much of a chance anyway of dealing with the full thing of the full spectrum of GR. But let's look at some of the basics of it. So a quick step into GR. And how is it different from SR? Well, I told you. All right, so this deals with accelerated motion. This is the general case of motion. And because accelerated motion is typically gravitational in a sense, this is thought of as a theory of gravity. So how does this happen? Well, this happens. And I'll make this arrow double-headed. How does one make this connection between these two things? And possibly it's pretty straightforward maybe in your mind, but let's put it into concrete terms. How does this happen? So in order to make this connection, let's consider two situations. Okay, and I'll do the accelerated motion over here and the gravitational motion over here. I'll start with the gravitational motion because that'll be easy. So here we are on Earth. We have gravitation on Earth, so no problem. We've got a rocket sitting here. And it's sitting here on a platform. It's being held up by these pillars here. So it's sitting there and it's ready to start blasting off, but it's not blasting off, it's just sitting there. Okay. And so what I'm going to do is, because this is a special rocket ship, we're going to have a window in the side right here. And because it's a nice sunny day here on Earth, because where do rockets blast off from? Cape Canaveral, in Florida, or somewhere like that, right? Windows open, we're enjoying some nice weather, and someone throws a baseball, and the baseball comes flying in through the window, and it makes a curved path in our gravitational field, right? So suppose that the baseball comes flying in here, and it drops because, that's the direction of things when we're here on Earth. We watch them take that kind of quote-unquote parabolic motion, and we say, yeah, curve downwards. Now, let's take that same rocket ship, let's close the window, and it's going to blast off. It's going to leave Earth, and it's going to go far away from any gravitational fields so that we are not thinking about gravity at all. We're completely able to concentrate only on accelerated motion. Okay? Now it's far away from any gravity. All right, this is far from gravity. This is on Earth, this one over here. I should label that. Okay, this is far away from any gravity. Here's the rocket ship again. And it's got its window right here. And we're going to flip the engines on, because if there were no engines on, then we would not have any weight, right? We wouldn't be pressed to the floor. So what we're going to do is we're going to accelerate the rocket upwards, which is going to accelerate the floor upwards, and I'm going to do it at exactly the same as Earth's gravitational acceleration. So this is going to accelerate upwards at g, which, if you like, is 9.8 meters per second squared. Okay. And that means the floor is accelerating upwards at 9.8 meters per second squared, and it's pushing me up, right? Which is essentially the exact same situation as if I was standing here on Earth. The floor is pushing me up, right? I push on the floor that way because I dent the floor that way, but the floor pushes me upwards, and so that's exactly what's happening here. The floor on the rocket is pushing us upwards. So we feel our normal Earth weights in this situation, just like in this situation. So if I throw a baseball through that window, if a baseball comes through that window, since the rocket is accelerating upwards, the path of the baseball would be straight, right? Because we're far from any gravitational fields. So the path of the baseball is going to do this. However, the rocket ship is getting faster and faster and faster going this way, which means that it looks like the baseball, instead of just going straight across, and instead of just going down in a linear sense, goes down in a curved sense, exactly as it does over here on Earth. Exact same trajectory. All right? Hopefully that makes sense so far. In other words, if I were to just drop a baseball while we were on the accelerating rocket ship, if I had an inertial view of this, right, if I was able to step outside the rocket ship and look, I wouldn't see the baseball moving. I would see the baseball just, when I let go of it, it stays right where it is. But the floor of the rocket ship comes up and bashes into it. So from the perspective of someone who is on board the rocket ship, it looks like the ball fell. And if we just tune the acceleration of the rocket ship, then it's exactly the same as what we have here on Earth. The path is identical when you then throw the ball. Okay, it dips down and makes the exact parabolic trajectory. Okay, this is all well and good. Let's just add one more thing to that, and let's do the same exact thing, but now with a light beam. Now through the window, instead of a baseball, I'm going to shine a light beam. But the rocket is accelerating upwards. The light beam would have gone straight across, right? But the rocket is accelerating upwards so that when light goes through the window, it does not go straight across the rocket ship. It curves just as the baseball curves because the rocket ship is accelerating upwards. Okay? So the light takes the same path, not with as much curvature, because light's traveling quite a bit quicker. Nonetheless, light curves. I'll just put it up here. So this is the baseball, and this is light. Light will curve through the rocket ship, not because light is taking a curved path, but because the rocket ship is, rather than going the same amount of distance per time, the rocket is increasing its distance per time, and that causes the path of the light, according to someone on the rocket ship, that causes someone on the rocket ship to measure the light taking a curved downwards path. But since we are saying accelerated motion is the same as gravitation, anything we see on the accelerated rocket ship, we have to see it on Earth here as well. And therefore, we will see light bent by Earth's gravitational field. Same exact thing. And this is known, ball here, ball down here, light down there. So light curves in a gravitational field because these two situations are equivalent, and because of that equivalence, this is known as the principle of equivalence. The principle of equivalence is exactly this. Accelerated motion is like gravitational fields, and vice versa. So whatever happens in one of them is going to happen in the other one. that means you can choose whichever way is the easier way to analyze something and do it that way, and then say, oh, it's going to happen that way also with the other way, with the other thing, right? So I can go to the accelerated motion reference frame and say, this is how everything happens, and then take all of that and say, that's how it happens with gravitation as well. And that's kind of the tack that Einstein used, but found that it got very difficult mathematically to do this. Now, the reason it got mathematically difficult to do that is because, okay, so if light is taking a curved path, but as we've talked about with the optics section and Fermat's principle and that type of thing, light basically always travels in a straight line, right? It travels in the shortest distance. Therefore, the shortest distance here on Earth must be a curved path. So, in fact, it's not light that's taking a curved path here. Light's going straight. It's that the space that it travels in is curved. Okay? And this is giving rise to the weirdness of the ideas of GR. What causes space-time to be curved and warped this way? It's the masses that exist in space-time. So the reason that space-time is curved around Earth is because Earth's mass is so big. Earth's mass being so big causes a gravitational warping of the space-time around Earth, which causes light to travel along those warped and curved paths. Because it doesn't know any better. It thinks it's going straight. But it's not. I guess. Depends, maybe. Does it depend on who you talk to? I don't know. Maybe it does. So the idea is that here that space is curved. And really, you to be proper about this, you say space-time is curved. Oops, is curved. And how do you find that curvature? Well, you find out how much mass there is in the vicinity. So the space-time is curved due to mass being here. And therefore, the sun curves space-time a lot more than Earth can. And that gave rise to one of the first tests of GR, which was done by Eddington a mere couple of years after the publication of the theory, which was that a star on the other side of the sun casting, right, which is emitting light, will cast two images, because ultimately, if the sun is warping the space by making a gravitational like bowl, what it's going to do is it's going to act like a converging lens, right? So one of the first tests of GR was this idea of gravitational lensing. And it's the idea that here on Earth, here's the sun. I'm going to put the sun like, say, here. And then there's a star that's way over here. The star is emitting light in all directions, so a lot of it's just bashing straight into the sun, and we can't see it. But some of the light does go kind of this way, and it gets curved by the sun. Some of it also goes this way and gets curved by the sun. Now, notice the light is curving towards Earth, just like it curved towards the bottom of this accelerating spaceship. Therefore, light is kind of, quote unquote, it's responding to a gravitational field. No, it's responding to curved space, but curved space is like a big mass in a bowl, right? So what the light's path here is going to be is it's going to start curving over like this, because the sun is going to act like a lens, and the light's going to take the shortest distance, which means it's going to curve around, follow the space-time, and hit Earth. Earth, therefore, is going to see two images of this star. In fact, it's not. It's going to see an entire ring around the star, around the sun, right? This is just the 2D representation of that. But the point is that you're going to see a light from a star, which you can identify clearly, and then you just wait 6 months until Earth is on this side of the sun, then you can see the star directly, measure the starlight, and go, oh, that was the same star that we were looking at that had the ring around it. This is known as the Einstein ring. And so what you see here is a large kind of star halo effect around the sun. These have been observed. Oops, they're not called halos, they're called rings. Einstein rings. And they have been observed, and they happen exactly as Einstein's equations predict they would happen. In addition to which, there are many other experimental tests that have happened that GR has given an answer which has agreed with the measurements. And it's because of this consistency in GR's predictions that we say this has to be some measure of truth. It keeps predicting the right things that we measure, right? And as you know, from a science standpoint, what do we care about? We care about agreement with experiment. As soon as GR messes something up, it's like, okay, see you later. We have to scrap most of this and fix it so that it does agree with experiment. But right now, it's been 110 years. We haven't found anything yet. Even down to I would say 5 years ago, but it's more like 8 to 10 by now, the existence of gravitational waves. Gravitational waves are a prediction of general relativity. And lo and behold, they were discovered, I think, in about 2016, 2017, 18, I can't remember, but it's right around, I'm pretty sure it was pre-COVID. And the gravitational waves were finally detected, which is, you're right, another prediction of GR which matched what the experimental results were. So there's a bit of truth in here somewhere in how he thought about this. So what else happens? You can test this, and in fact, I kind of started to mention this, maybe, I can't remember whether it was this class or the live class, but in one of those classes I mentioned, somebody did an experiment involving shooting light straight upwards in a gravitational field in order to test the energy, kind of the energy equivalence. But what happens when you shoot light straight upwards in a gravitational field is that it's trying to leave a gravitational field, which means some of its energy is kind of going into trying to leave the gravitational field. In a classical sense, you talk about the increase in potential energy that happens. And what you find is that light indeed loses some energy traveling upwards in a gravitational field in order to try and leave. And so the light becomes Doppler shifted. The light actually is a lower energy by the time it reaches a higher point. Now I'll give you one other situation here. Since we talked at length about time in SR, let me give you some time in GR. Let's suppose we have a turntable. And the turntable has 2 clocks on it. I don't know, or those bugs. Well, they're supposed to be clocks. So the turntable has 2 clocks on it, okay? And the turntable, okay, has a rotational axis, say here, and is rotating around like this. Counterclockwise as seen from above. Now, this clock here is stationary with respect to us, right? This clock here, if I am standing here watching this turntable spinning around, that clock is not moving. So this clock is in my reference frame, and so therefore this clock will not be dilated. However, when this clock passes from, say, here to here as it goes around, and then from here to here as it comes back, it is in relative motion with respect to me. So I see it going like this, right? It's going like this, which means I'm basically looking at it going back and forth. It's always in relative motion with respect to me, except for near its edge points, which means its time should be dilated. This time should be dilated because from a special relativistic point of view, it's in relative motion with respect to me. Therefore, these two clocks should read different times. Okay, but what if I jump onto the turntable with this clock in front of me, and then that clock right there, right? I'm looking at that clock. So I jump on here and I'm staring at that clock, and we're going around, but that clock, if I point at the clock, that clock never moves. Yeah? The clock was always right there. So special relativity won't work here because there's no relative motion. But what we do find is that there's an acceleration on this clock. This clock is feeling an acceleration, a centripetal acceleration, to keep it going around on the turntable. And so GR would say, well, if you are now in an accelerated reference frame, the time that you're seeing is going to be slower. And therefore, if it's accelerated reference frame, slower time, therefore it's gravitational field, slower time. And that means that people in deeper gravitational fields experience less time than people who are out in free space. All right, so clocks in gravitational fields run slower than clocks that are outside of the gravitational fields, right? Like we would say moving clocks run slow. Well, clocks in gravitational fields run slow. And someone in the class the other day reminded me of a scene in that movie with the black hole, right? And the black hole has such an intense gravitational field nearby that when you go near it, as seen from someone who's far away, the clocks of that ship are going to be running slower if it's near a black hole gravitational field, which is much more intense. So they will experience less time. Then they come back out and they have essentially the exact same situation as the people who fly away on the rocket ship and come back. The people fly away, turn around, come back, and they have not aged as much as we have aged. Same thing happens in a gravitational field. You go down, spend a bunch of time in a gravitational field, come out, you will have aged less than the people who are outside the gravitational field or in a weaker one, right? So it's nice that we're down here on Earth because our clocks are dilated compared to the satellite clocks, right? Satellite clocks are in orbit around Earth, the GPS satellites, and they're experiencing something like 3 to 4% less of a gravitational field than we are. So those clocks are running faster than our clocks are, or vice versa. They would say our clocks are running slower because we're deeper in a field. Anyway, a couple of consequences of general relativity. By no means did we even scratch the surface of this. There is a lot more that's involved, but nonetheless, I hope you enjoyed a little bit of an introduction to that. And we'll call this the end of our relativity section, which means tomorrow we're starting the quantum mechanics section, and we're going to go from there. All right, so I wish you a wonderful relativistic rest of your day, and I will see you tomorrow. Get started on that homework, and don't leave it all to the last minute over the weekend, so that at least you can have some time to relax over the weekend. All righty, folks, we will see you next time.